Last time we talked about regression analysis. We started talking about regression analysis. And what I tried to do was overview the logic of regression analysis, and then we went through part of the process of regression. What I would like to do today is to summarize, to review some of the material that we talked about last time, and hope that it becomes clearer, and then finish out this discussion of regression analysis today and potentially next time. As I indicated to you, regression analysis is dissimilar to analytic procedures like analysis of variance, where you're testing for between-group difference. What regression analysis allows you to do is to forecast, to predict future outcomes based upon past outcomes. The first step in this process was to generate the line of best fit, specifically, since we're dealing with simple regression, the straight line of best fit through a set of data points. And those data points exist in two-dimensional space. That is, there's an x-coordinate and a y-coordinate. Two things. One, those data are known data. Sometimes known from the past, sort of archival data, and sometimes known because you've just collected that data from participants in research. Second, the X data represent the predictive variable, and the Y data represent the outcome variable. As I've indicated, the first step in this process is to generate the straight line of best fit through those known data points. What we observed, even with a simple, very simple data set involving 3 data points, was that it's unlikely that all of the data points will line up will array themselves in a straight line. That is, whatever line you generate through the data set will miss some or potentially all of the data points. This implies that the line of best fit involves error. And we discovered that generating the line of best fit involves minimizing that error. In fact, it means that line of best fit is generated by invoking what is called the least squares criterion. And the least squares criterion is simply a requirement to minimize the sum of the squared error between actual and predicted y-scores. That is, to minimize the sum of yi, the actual y-scores, minus y hat I, the predicted y-scores, squared. This is the least squares criterion. And if you invoke the least squares criterion, you can generate a single straight line that minimizes the amount of squared error better than any competing straight line. That is, you can generate the line of best fit. Are there any questions dealing with either the overall logic of regression or more specifically with the line of best fit and the least squares criterion? If not, let's look at an example. If this is the line of best fit, the straight line of best fit through a data set, whatever that data set looks like, the form of the equation that describes that straight line is y equals a plus bx, where a is the y-intercept, that is the point at which the line intersects the y-axis, and b is the slope of the line. B indicates the amount of change in y per unit change in x. And we'll work through some examples of this. You will not have to calculate either A or B. What you will need to do, other than knowing the sorts of underlying issues in regression analysis, like the line of best fit, like the least squares criterion, and so forth, is to interpret regression equations. And this is straightforward. This is somewhere back in, I don't know, 5th grade or 4th grade or whatever grade it is, but somewhere way back. You know something already about the slope of the line B. What is B likely to be related to? Another concept or construct that we've examined in here that deals with the slope of a line. Let me give you a clue. If the resulting regression equation was of the form y equals a minus bx, what would be the direction of the line? This way? Yeah. How did you make that conclusion? Because there's a negative slope. Isn't this then associated somehow with Pearson product moment R? We observe when talking about Pearson product moment R that if the value of R was positive, then it indicated a positive or direct relationship between x and y. That is, as values of x increase, values of y increase. And that if R assumed a negative value, it indicated a negative or inverse relationship between x and y. That is, a relationship in which high values of x are associated with low values of y, and low values of x are associated with high values of y. So somewhere in the computation of B, R is involved. And I indicate that not, as I've suggested to you before, not because you will be called upon to compute some value of B given some value of R, but to indicate to you that there's some link between correlation analysis and regression analysis. And the link is this link between Pearson product moment R and B, the slope of the line. What remains in regression analysis is incredibly straightforward, and we could probably discuss this in a minute and a half. If you collect data, that is, if you collect real X scores and real Y scores, and then you subject those scores to regression analysis, the output will be some regression equation. A regression equation that takes this form. Let us presume that the regression equation from some hypothetical set of data is y equals 6 plus 4x. Would you agree now that if you were to go out and collect new X scores, you could predict the associated Y scores? Yeah? So that if X equals 2, Y equals 6 plus 4 times 2, would you agree? Hang on people. I'm sorry. No baby. God, I hope future students who watch this are enjoying this as much as I am. I was already halfway to Austin, you understand. Pardon? I'm just getting myself back into the mode, you know? You can use this regression equation to take new values and known values of X to predict unknown values of Y. So that if the regression equation is Y equals 6 plus 4X, then if X equals 2, Y equals 6 plus 4 times 2, that is X assuming some real value, which is 6 plus 8, which is 14. Yes? This is straightforward, right? I mean, this is... When you signed up for this course, did you really think it could be this easy? You know? And yet it's magic. It's magic because most people are too afraid to sign up for the course. See? You will go out with levels of knowledge. You will be so statistically sophisticated, you will rate in the top 10%. Again, using the same regression equation, if X equals minus 2, then Y equals 6 plus 4 multiplied by minus 2, which is 6 minus 8, which is minus 2. Yeah? Is that right? One observation then about regression analysis and regression equations. Regression equations can generate impossible answers. That is, it may be impossible. While you and I can draw this, yes, we could draw a line that intersects the y-axis in this way at some point below 0. It may be in reality impossible for y to assume a negative value. For example, in the text there's an example offered that links number of prior arrests with length of prison term, where number of prior arrests is the x-score, the predictor value, and length of prison term is the outcome variable y. It is impossible, clearly, for y to assume a negative value because you cannot receive a prison sentence of less than 0 minutes or hours or days or whatever it may be. It is possible, however, for regression equations to generate that sort of answer, as is the case here. To generate values of y that, while theoretically possible, are practically impossible, are in reality impossible. Why would that be the case? Let's even use the example in the text. Between the relationship between number of prior arrests and length of prison sentence. Why might our analysis generate a regression equation that, given some values of x, would generate negative values or impossible, practically impossible values of y?
So do you say if negative values of x produces positive values of y?
No. Well, let me get rid of all of this while I'm rephrasing the question. The overall, the fundamental issue is this. We found it easy enough, I hope, to generate and interpret regression equations. It involves generating the straight line of best fit. You do that by invoking the least squares criterion. When you apply the least squares criterion to a set of data, it generates a straight line of best fit, and what's more, it generates the equation that describes that straight line. We know that the form of that equation is y equals a plus bx, where a is the y-intercept and b is the slope of the line. And it's very straightforward to plug in actual values of x and use those actual values of x with the regression equation to predict unknown values of y. That's what we did in 2 examples here. The point I've made is that, or the observation I've made, is that regression equations, given some real values of x, can generate what are theoretically possible, but in actuality impossible values of y. For example, it is possible to use the data dealing with number of prior arrests and length of prison sentence to generate a regression equation. But it is possible that that regression equation will generate practically impossible values of y, prison sentence, even though the values of x are real values. You can't have a prison sentence of less than 0, but it is possible for you to generate a regression equation, given the specific nature of the data you use, that will nonetheless generate negative values or impossible values of y, even though the values of x are real. Why would that be the case?
Is that depending if they're positively or negatively correlated with each other?
No, it doesn't. It's not associated with the negativity or positivity of the relationship between the x and y scores. It has much more to do with the strength of the relationship between the x and the y scores. We became accustomed in analysis of variance to talking about explained variance and unexplained variance. And we had one variable that explained variance. It was the independent variable. The rest of the variance remained unexplained. Unexplained at least by this independent variable. What explains the rest of this variance? I need help. Take any aspect of your behavior. How often is your behavior a function of one and only one variable acting on you? Let me rephrase that. Look at your own behavior. How often is your own behavior a function of one and only one variable acting on you? All the time? I hope you mean none of the time. It's unlikely. We simply, in the normal course of events, do not encounter situations where in which our behavior is a function of a single variable. You make choices about going to see a movie. That choice is, I suspect, based upon multiple variables. Who you're going to the movie with, the availability of the movie at a particular time, reviews that you've read of the movie. Other sorts of behaviors. Your liking for another person. I suspect that your liking for another person could be based upon your ability to predict the other person's behavior, your perceived similarity with the other person, the frequency with which you see the other person in a routine sort of way, the potential reward, what you perceive as the potential reward value of the other person. That is a number of variables acting on you in conjunction. it's rare that our behavior is a function of a single variable. The point that I'm trying to make is that besides the rest of the variance, that is, besides this explained variance, this unexplained variance can also be called error variance. And obviously error variance or unexplained variance increases as the relationship between what we've in analysis of variance called the independent and the dependent variables diminishes. Yeah? Or no?
So it's independent or dependent?
Can I say it again? I can say almost anything again. In fact, even without being asked, I say things repeatedly. Sometimes I don't even know it. I probably have told the same stories to people 100 times. If you have a very strong relationship between the independent and the dependent variable, the independent variable will explain a substantial portion of the variance in the dependent variable, yes? If you have a relatively weak relationship between an independent and a dependent variable, the independent variable will account for substantially less of the variance in the dependent variable. If we now switch to the language of regression analysis, I indicated to you that B, the slope of the line, was related to R. We've looked at R before, and we've talked about shared variance. That is, if the correlation between X and Y is minus 0.5, then the amount of overlap between X and Y is R squared, which is 0.5 squared, which is 0.25. That is, 25% of all of the variance in X and Y is shared. If R is 0.05, then R squared is 0.0025. Yes? That is less than 1% of all of the variance in X and Y is shared. First of all, are there any questions about this issue of shared variance? The general point I'm trying to make is, as the relationship between an independent variable or a predictor variable and the dependent variable or the outcome variable increases in strength, the predictive value of that X score increases. There is a stronger relationship between the predictor value, the predictor variable, and the outcome variable. Let me approach this another way. Let me say the same thing in a different way. I argued moments ago that your behavior, Y, is typically not the a function of a single variable acting on you, independent of other variables. That is, your behavior is more typically described as a function of A plus B1 x1 plus B2 x2 plus Bn xn. Yes? That is that your behavior, y, is typically a function of multiple variables acting upon you simultaneously. Is there anybody who does not either understand that argument or B, disagrees with it? Would you agree, given this argument, that some of these variables acting on you exert more strength on your behavior, more influence on your behavior than do other variables? You have to give me more help than this. You know, I'm out there cycling away. But when I look round, I'd really like to see you somewhere close, you know? When you decide that you want to go to a movie, what sorts of things influence your selection of which movie you'll go see? This is not a hypothetical question. Who's in the movie? Who you're going with? The type of the movie? How long the movie is? Where the movie's showing? How far away the movie theater is? Other things you might do instead of going to a movie? Typically, well, let me ask as an intermediate question. Do all of these variables influence your decision equally? Some exert more influence on your decision than others. Yeah. So the relationship, the strength of the relationship between X1, who's in the movie, X2, how long the movie is, X3, what type of movie it is, and so forth, and the outcome, whether to go to the movie or not, those relationships are not equal in strength. Yes? Is it not rather simplistic then, first of all, to seek to predict an outcome on the basis of a single variable? This is like trying to explain your decision about whether to go to a movie or what movie to go see based only upon what type of movie it is. Even if you don't like horror movies, there's some likelihood that you will go to see a horror movie under some conditions. Every guy in here has been to a chick flick. Yeah? One of those things about love and relationships and where everybody's talking about their feelings and oh God. And all of those stories, they go on for like 3.5 days. You know, the movie lasts 3.5 days and you're having a coronary, but you're going to see it anyway. Because the person you're with wants to go see it and you'll do anything for them, including seeing a movie where they talk about feelings and there's no gratuitous sex or violence. No. I'm really struggling to make the point that it's absolutely simplistic to try and predict an outcome based upon a single variable. What is more, the variable that we select may have a relatively weak relationship with Y, the outcome. Whether or not they sell water at the movie theater. And why is it that so many women, when you go to a movie, you say, well, would you like something? Yeah, I'd like a bottle of water. Oh, good. Yeah. Like you've just selected the most expensive thing on the menu. It's like going into a restaurant and saying, what would you like? Oh, I'd like the lobster. Oh, good. And I guess you'd like an expensive bottle of wine with that too. Why is it that in a movie theater a bottle of water costs like $9.25? I don't get it. Is it like being in the middle of a desert? Is this a particularly arid place? My decision about movies is only weakly related to whether they sell water there or not. I'm more likely to go to a movie theater where they don't sell water than to one where they do. If that's the case, you see that this X variable explains very little of the variance in Y. The relationship between X and Y is very weak. What that means is that I, which is all of the rest of the stuff, that is the error in the equation, will be great. If the relationship between X and Y is very weak, the error involved in the regression equation will be substantial. Given that, do you understand, at least intuitively, that the predictions based upon X will also be laden with error? Yeah? And if that's the case, it seems to me not unreasonable to suppose that in some situations that predictor variable will generate what are practically impossible values of Y, simply because the error involved in the prediction is large. One would expect that your predictions would become increasingly accurate, first of all, to the extent that these X's explain a substantial amount of variance in Y, and to the extent that you had multiple predictors of Y. the more information that you have about the relationship between X and Y, the higher the predictive value of the X information. Yeah, I'm saying the same thing actually over and over again here in different sorts of ways. I sense that there is little difficulty associated with understanding, generating the single straight line of best fit. Little difficulty in understanding the least squares criterion, and little difficulty in using regression equations to predict values of Y given a real value of X. What started all of the misunderstanding, or all of the difficulty here, it seems, is my observation that under some circumstances the outcome of applying a regression equation can be impossible. That is, given real values of X, you can some regression equations will generate unreal values of Y. Values of Y that cannot be achieved. The question then is, under what conditions would that happen? And I've tried to show you in 2 or 3 roundabout ways that it can happen when, first of all, it's more likely to happen when the relationship between the predictor variable and the outcome variable is weak. And second, it's more likely to occur when you have few predictor variables, and we are using the archetype of that case. We're using one predictor variable. It's less likely to happen, it's more likely to happen when you're using few predictor variables as opposed to many predictor variables. Would you, well, I'm trying to get at the same issue again here. If you apply to law school, you will have to provide multiple pieces of information. You will have to provide an undergraduate transcript. You will have to, which will include 2 things. One is an overall GPA, the second is GPA in the last 60 hours, and the third is GPA in your major. So there are 3 pieces of information there. You'll have to provide an LSAT score, which will include multiple pieces of information. You will have to provide letters of recommendation, which provide additional pieces of information. And you will have to provide some statement of purpose, which provides further information. You provide that information so that the persons who make the decision about whether to admit or not to admit you into law school feel confident in their predictions. And the more pieces of information they have, the more confident they feel in their predictions of your success or failure in law school. It seems to me that that's consistent with the logic of regression in specific, but it's consistent with a general model that you and I have of decision making up here. If the decision to admit you or not to admit you to law school was simply based on your LSAT score, some of you would object. And you would object on this basis. I'm not good at those sorts of tests. Or I didn't feel well that day when I took the test. What you're arguing is that the relationship between your specific LSAT score and your success or failure in law school is a weak one. For any of several reasons. And that, so that the prediction that's being made is laden with error. That error would decrease to the extent, first of all, that multiple predictors were used, and second of all, that those predictors shared a strong relationship with the outcome variable. To the extent that you use few predictors, and to the extent that those predictors are only weakly related to the outcome variable, the likelihood, or first of all, the regression equation is laden with error. So that second, it's possible to generate what are practically impossible values of the outcome variable, even though the values of the predictive variables are real. Yeah. Go away. No, I don't mean go away. I mean go away and think about regression analysis. If you have questions, I'll answer them next time. Don't show up for the exam going, I still don't understand this stuff. Okay? I will answer your questions next time.